So in this video we will understand about that what are the electronic property that cannot be explained by the wave function or by the wave nature of the electron. So there are three observed properties associated with the how atom interact with electromagnetic radiation cannot be explained by the waves. So number one is the emission of the light from hot object. For an example, lightning of the bulb, because when the bulb light it heat, and when it heat it shows some light. So this property was not explained by the wave nature of electron. Second was emission of electron from the metal surface on which light is shone. So that phenomenon is called photoelectric effect. So according to this, if you have a metal and if you are shining a light, intense beam on the metal, and metal releases the electrons, so this is called photoelectric effect. Photo means light and electric means current. So this effect was also not explained by wave nature of the electron. And the third one was the emission of the light from the electronically excited gas atom or emission spectra. So we will see one by one. So these are the three properties which were not explained by the wave nature of electron. So let's see one by one what are those. So first was the wave nature of light does not explain how an object can glow when its temperature increases. For an example, this picture shows that when you heat this iron nail, it start glowing like a red and yellow. So this type of phenomenon was cannot explain by the wave nature of electron. Number two is, and this is the same example, then this is in our kitchen. When we heat the coil, it starts shining the light, and the bulb also. So these were the two examples. Third example was the photoelectric effect. When a photon hit the surface with energy, they emit electron from the surface. So that effect is called photoelectric effect. So Einstein used quanta to explain the photoelectric effect, and this effect was explained by scientist Einstein using the term quanta. And what is the meaning of quanta? We will see. Each metal has a different energy at which it ejects electrons. At lower energy, electrons are not emitted. So you need higher energy to give the electrons, then they can emit out. And he concluded that the energy is proportional to the frequency. So how much energy is required to emit one electron, which is equal to h nu. This is again nu and u. So nu is frequency, where h is a Planck constant, which is 6.626 times 10 to the power minus 34 joule second. You need not to remember this one, memorize this one, but it will be given in the questions whenever the Planck constant question will come. So this was the effect which was also not explained by the wave nature of electron. And in continuation of this photoelectric effect, so as Einstein has explained the relationship between the energy and frequency, E is equal to h nu. So, and we know in the previous slide that nu, which is frequency, and nu is equal to c over lambda, where c is light, speed of light, and lambda is wavelength. So we can also replace nu with the c over lambda. So energy can also be equal to hc over lambda, where h is the Planck constant and c is speed of light, and energy is in the photon. So you have to remember this these two formulas actually, and there will be some questions, there will be some numerical question related to these equations. So where you can find out that how much energy will be required to remove the one electron, or if any wavelength of light is coming, that how much energy will it have. So Planck quantum theory in 1900, matter can emit and absorb energy only in the whole number of multiples of h nu, such as 1 h nu or 2 h nu, 3 h nu, and h nu is called quantum. So and many quantum, many, it's a plural word, is quanta. So matter can emit and absorb energy. So any matter can emit or releases the energy in the form of quantum, and one quanta is equal to h nu, and it can emit either one quanta or two quanta or three quanta, or it can absorb one quanta, two quanta, and three quanta, like that. So and Einstein says that energy level in tiny particles are called energy packet, or called photons. So whenever the light comes, as you can see in this picture, that when the light emit the metal, it is emitting in the form of, when light is hit on the surface, it is hitting in the form of h nu, which is called quanta, and these energy comes in the form of packet. So that packet is called photon. Photon, the term was given by Einstein. So these phenomenon, which was not explained by the wave nature of electron, were explained by these quantum and energy term. So let's see one question, practice problem, which is one type of sunburn occur at exposure of UV light of wavelength in vicinity of 325 nanometer. What is the energy of the photon of this wavelength? So in this question they are saying that if a sunlight is emitting 335 nanometer wavelength, or any UV light, which is basically this is the UV light 325 nanometer. So you can see this vicinity of, so wavelength is given, lambda is given, which is 325 nanometer, and they are saying that the energy of the photon so will be how much. So how we can calculate? So since, as we have just seen the previous relationship, that E is equal to h nu, nu is the frequency, and we know that nu is equal to c over lambda. So we can replace this nu value here. So energy will equal to h c over lambda, where h is the Planck constant and its value is 6.626 times 10 raised power minus 34 joule second. So this is the h, and then c we know that which is speed of light, which is 3.0 times 10 raised power 8 meter per second, and then lambda will be in wavelength is lambda is given 325 nanometer. And so you can see we have a nanometer here and we have a meter here, so we have to convert this nanometer into meter. And 1 nanometer, sorry, it's a small n, 1 nanometer is equal to 10 raised power minus 9 meter, right? So let's try to solve this one. I will solve like this equation. Let me just simplify this first. Second will be cancel out, nanometer and nanometer will be cancel out, meter and meter will be cancel out, only joule will remain. So this I can write like this: 6.626 times 10 raised power minus 34 and multiplied by 3.0 times 10 raised power 8 and divided by 325 multiplied by 10 raised power minus 9. So let's try to solve this. 6.626 multiplied by, oops, it's not started yet, now it will come. 6.26 multiplied by 3 will be equal to 18.78 times 10 raised power minus 34 times 10 raised power 8. I'm moving this 10 raised power minus 9 to above, so this will become 10 raised power plus 9. So divided by 325. So 18.75 divided by 325 will be equal to 0.0578 times 10 raised power, see, this will become 8 and 9 17, so this will become minus 34 and then 10 raised power 17, so 17, this will become 0.0578 times 10 raised power minus 17, because we will subtract 34 minus 34 to 17, this will become minus 17, and then once again these decimal place will go on the before 5, so answer will come 5.78 times 10 raised power minus 19 joule. So this much energy will be coming out from the UV light. One type of sunburn occur on exposure of UV light of the wavelength in the vicinity of the 325 nanometer. If we are in contact with the 325 nanometer of UV light, it will be giving us 5.76 times 10 raised to minus 19 joule of energy. You can see how small energy is, but still it is enough for us for the sunburn. Therefore we have to keep away from the UV light. So this was a slide based on the expression of the energy and wavelength and Planck constant. And next is the nature of the energy, which is called the quanta. Max Planck, it was given, the Planck constant was based on the Max Planck, and Max Planck explained it was assuming that the energy come in the packet called the quanta, which and in singular form is quantum. So for an example, if we are going upstairs, so we go one by one stair, so you can see it's written potential energy of a person walking up ramp increases in the uniform in continuous manner compared to potential energy of the person walking up stair increases in stepwise quantized manner. So potential energy of this person is increasing continuously, and here potential energy of person is increasing in quantized manner. As many as the stair he will go up, he will get that much of energy, because every step is quantized. Quantized means fixed, that how many steps you have completed. So that is why the energy is expressed in the form of quanta. And another exception was the line. That this was the third example, that one thing was not able to explain that how the metal glow. So according to this slide, how the emission of the light from the hot object, which was not explained by the wave nature of the electron. Second was the emission of electron from the metal surface, and which was called photoelectric effect. And third was the emission of the light from the electronically excited gases. So this was also not explained. So let us see what is this one. So another mystery in the early 20th century involved that emission spectra observed from the energy emitted by the atom and molecule. So here are the two examples, two pictures are shown, like a neon gas. This is neon gas. It shows as a line spectra, orange color line, and hydrogen gas shows like a purple color or blue color line spectra. So these two this phenomenon was also not explained. One cannot explain by the wave nature of the electron. So continuous versus line spectra. What is the difference between the line spectra and continuous spectra? So if you remember that if you have a white flashlight, so white flashlight contain all 7 visible color, and because when you will pass it from the slit and prism, you can see the visible spectrum, which is called Vibgyor. And this type of spectrum is called continuous spectrum. So for an atom, so this was the continuous spectrum, which was coming from the white light. But for an atom and molecule, one does not observe a continuous spectrum, the rainbow like spectra, and as one get from a white light source. So what type of spectra we got from the atom of a molecule? Only a line spectra of the discrete wavelength is observed. Each element has the unique line of spectra. So these are the different line spectra has been shown, and these lines have different atoms or different elements. And here in this case, the hydrogen spectrum shows 3 line, which is near, I think this is 4 line, 1 2 3 4 line shows. So it was discovered in 1885 that simple formula related to 4 lines of integer. So how to interpret these and what will be the energy of these spectra, hydrogen spectra. So these scientists, Jonathan Balmer and Redberg and Neil Bohr, they studied the hydrogen spectra very detailed. So we need not go in the very detail about this one. And they established a mathematical relationship between the wavelength and their number of lines. So these were the 3 properties which was not explained by the wavelength, wave nature of the light. Therefore, a new theory came, which is called the quantum mechanics. So quantum mechanics and theory came to explain these phenomena, and we have seen the quantum means energy, which is the packet form of energy. And so energy, the term energy term explain these phenomenon very well, and we will understand these development of quantum mechanics in the next video.